So reminder from yesterday, guys, that the key points for circular motion, okay? First off, that there's a number of multiple choice questions about how circular motion works, okay? Object is accelerating always towards the center because there's a force, a centripetal force, pulling it towards the center, okay? That the velocity as a result is always changing, but the speed is constant. Okay, so knowing those kinds of things, problem solving, all right, we did bank curves, we did unbanked curves, those are all important, okay? Then we talked about artificial gravity, then we talked about vertical circular motion, which is different, it's not uniform, the speed does change throughout the circle, fastest at the bottom, slowest at the top, forces change, okay, throughout the vertical circle as well, gravity is either pulling in or out depending on where you are. And then we talked about gravitation, so Newton's universal law of gravitation, right? Make sure we can calculate force of gravity, Jen and Emily. Okay, and then we got satellite motion after that, okay, Fc equals Fg, and then gravitational field strength after that. So, okay, those are all the key concepts for the circular motion unit. All right, anything you want to ask or have me go over from circular motion right now? A satellite question, okay. I was gonna do one where I had to substitute. You read my mind. Okay. Okay. So it doesn't seem like I give you very much information in that question. Okay. It's because I quite frankly don't have to give you very much information in that question. So we are looking for the altitude. Is altitude one of our tricks for satellites? Yes, okay, that's wanting the height above the surface, meaning that when we do finally get the orbital radius, which is what we'll be looking for, okay, then we have to do what with the Earth's radius from that number? We have to subtract it, all right? So we do know we have to do that. And we're told that it's orbiting Earth, all right? So I indirectly tell you that you need to use the mass of the Earth and radius of the Earth and things like that, okay? And it has a period of 16 hours. So let's, first off, what do I have to do with that period right now? Can I use it in hours? And if I'm using Fc equals Fg, I'm using newtons equals newtons. And a newton is a kilogram meter per second squared. Okay, so I need to turn this into seconds. So 16 times 3600. All right, so 57,600 seconds is the period. All right, so we have Fc equals Fg, and that's going to be Newton's universal law of gravitation, okay, not m times g. So we're going to have mv squared over r equals big G times the mass of the Earth times the mass of the satellite over r squared. Which mass is this one over here? Mass of the satellite, because what's going to happen to the mass of the satellite? It's going to cancel, right? On a test, I would probably tell you the mass of the satellite. Why? Well, not because I hate you, but because I'm inherently mean, okay? And I would want to make sure that you know that the mass of the satellite is actually not an important number. Test whether you know your significant digits or not, okay? Because I might make it a different number of significant digits and see if I catch you on that. The fact that you don't use it means, okay, that it doesn't count, all that kind of stuff. So there's all kinds of little subtle things, okay, that I might do on a test that are testing more than one thing in a question, right? Sometimes a question is not just satellites, it's also a significant digit question. Okay. All right, so right now we know we can't use mv squared over r because we don't have v and we don't have r. So there's no way for us to calculate it. So what we have to do is substitute in v equals 2 pi r over t for v, right? But first we have to square it. So that's going to be 4 pi squared r squared over t squared. Now we're going to plug that in to this formula. So I'm going to have m 4 pi squared r squared over t squared times r. So what's going to happen with those r's? They're going to cancel. So the one on the bottom is gone, the squared is gone from the top. All right, and that's going to equal, again, g times the mass of the satellite times the mass of the Earth over r squared. All right, right now I'm going to take the mass of the satellite out of there because I know that it's going to cancel anyway, at least one less thing for me to move around. So I'm trying to solve right now for the altitude, which means I need r. Okay, so I'm going to bring the r squared from the right-hand side, bring it over to the left-hand side by multiplying it. What's r squared times r? R cubed. Okay, so that r is gone, and it's now up here. Okay, we have r cubed. I want to move everything else over to the other side because r is what I'm trying to solve for. So I'm going to multiply both sides by t squared. So it's over there. And then I'm going to divide both sides by 4 pi squared. Okay, that leaves me with r cubed. I want just r. All right, so I'm going to take the cube root. Right? And one of the most common mistakes on a question like that would be to accidentally square root instead of cube root. Okay, so now we're going to plug in our numbers here. So we're going to have that r equals 6.67 times 10 to the minus 11, so big G, times 57,600 seconds, and that's squared, times 5.98 times 10 to the 24, that's the mass of the Earth, divided by 4 pi squared. Right? So that should give us the radius if we cube root it. Whoop, missed a bracket. Okay, now I have to cube root that, so math 4, the answer. Okay, so my orbital radius is 3.2 times 10 to the 1, 2, 3, 4, 5, 6, 7. Okay, that's 10 to the 7 meters. Now, what else do I need to do here? What's that? I need to subtract the radius of the Earth, right? Okay, so I'm going to take that number, okay, and to get the altitude, I'm going to go 3.22, and I'm going to keep all those decimals, guys, times 10 to the 7 meters minus 6.37 times 10 to the 6 meters. Okay, so it's got an orbital altitude of, and I think I only have 2 significant figures here, so 2.6 times 10 to the 7 meters. Okay. So that one has basically everything that a satellite motion question could have in it to make it tricky. Right? It had the altitude thing, it had the substitution thing, it didn't give you very much information, just the period, okay, all of that kind of stuff. So that would make one fairly tricky. Okay, what else? All right, so we have a bank curve question, let's say. In this one, we're going to look for the speed. All right, so I have that this is a 250 meter bank curve. If I write it like that, I mean that that is the curve's radius. Okay, not the circumference, it's radius. Okay, and we know that it's banked at 9 degrees. So we know what theta is, and we know what the radius is, 250 meters. Okay, so we are looking for what speed it can be negotiated at. All right, so the bank curve formula is tan of theta equals v squared over r times g. Right, so if we're looking for v, we multiply both sides by rg, so we have the tan of theta times rg equals v, and we have to square root that. All right, so when we plug that in, we'll have the tan of 9 degrees times 250 times 9.81. Whoa, not second tan, it's tan. 9 degrees. All right, so we could take that corner at 20 meters per second because we only have two significant figures. Okay. That makes sense, Kelly? Yep. I did 2 of those in period 3 yesterday. Okay, I'm going to give you guys a couple minutes to try that one. I want the acceleration of the box. Okay, I want the acceleration of the 10 kilogram box, given that it is being pulled by a 120 Newton force angled 20 degrees above the surface. It is not moving in 20 degrees, it is sliding along the table. All right, I want you guys to find its acceleration. Okay, give you guys a few minutes to see if you can figure it out, and then I'll go over it. So what we've got here is we've got this 10 kilogram mass being pulled at 120 or with 120 newtons. Okay, but the trick to this question is actually identifying all the other forces involved. The box is not moving that way. It's moving horizontally. So what I need to do is first break that 120 up into its horizontal and vertical components, okay? Because those are the parts that are going to matter to me in this question. All right, so I'm going to have, okay, this that we'll call F horizontal, and this that we'll call F vertical. Okay, they're the horizontal and vertical components of our 120 Newton force. Okay, so we're going to take our 120, so we'll go sine 20 times 120, that'll give us the vertical side, so 41.042 newtons. Okay, and then we'll find the horizontal side, so cos of 20 times 120. So that side's going to be 112.763. Okay, so we've got those. Now I need to finish my free body diagram. What other forces are acting on the box? Gravity. Okay, what else? Friction. Okay, what else? Yep, normal force. And for the vertical force that we calculated over here. Okay, we have the horizontal force kind of already drawn on here, which essentially now means we don't need that 120 Newton force anymore. We've already figured out what its contributions to this whole system are. All right, If I want to find force of friction, and I'm going to need that because it's sliding along the table, to find the acceleration, I definitely need to know the value of this force. I'm going to need normal force because that's part of friction's formula. How do I calculate the normal force? Right, gravity minus the vertical force. Here's why. Okay, is the box moving vertically? Then the net force vertically is 0. All right, so that means the forces up add up to equal 98.1 newtons. All right, so all I have to do is subtract from 98.1 what my force vertical is. All right, so that leaves me with 57.058 newtons. Okay, now that I know that, I can calculate force of friction. So I'm going to go 0.275 times 57.058. All right, so we're going to have 15.69 newtons worth of friction. Okay, now that I know how much friction there is, and I know how much forward force there is, can I find the net force for the box? Right, so I already know that this force, and that force add up to 0. Done. I don't have to worry about those forces anymore. Okay, I've already taken care of this force as well. Okay, all I have to worry about are the horizontal force forwards and the force of friction backwards. Okay, so to find the net force, I'm going to use the vector sum of all forces and go F horizontal plus the force of friction. So that's going to be 112.763 plus negative or minus 15.69. All right, so that leaves me with 97 newtons as my net force. And then when I want to find acceleration, okay, I go acceleration equals F net divided by m, or F net equals m times a, right? And that'll give me the acceleration, which should be 9.7 meters per second squared along the table. Okay. We did a number of questions like that in that unit, and there was one like that on your unit exam. Okay, so certainly it tests a lot of things. It tests some vectors, it tests friction, forces, all that kind of stuff. So something like that is, a question that tests multiple things. All right, Kylie, you wanted a pulley question, right? So like a vertical pulley or one where there's a mass on a table and the pulley's hanging? Matter? Okay. All right, so I have this vertical pulley, and I'm holding on to the 7 kilogram mass so that the pulley won't move. If I let go of the 7 kilogram mass, obviously it's going to fall and the 4 kilogram mass is going to rise. I want to find the acceleration of the 4 kilogram mass. I'm going to give you a minute or two on that one. Okay, I want the acceleration of the 4 kilogram mass. Okay, what was tricky about the way I asked this question? I asked you for the acceleration of the 4 kilogram mass. Right, the whole system accelerates at the same speed. The 7 kilogram mass, the 4 kilogram mass, they're attached. They can't accelerate at different rates. One is causing the other to accelerate. Okay, so we're actually going to find the acceleration of the system and then just apply the proper vector up to the 4 kilogram mass. Okay, had I asked for the acceleration of the system, you wouldn't have been able to put a vector on that because the parts of the system are moving in different directions. All you'd have been able to do was give me a value, a magnitude. All right, so we have to identify the forces that are acting here, right? We got a force of gravity here, and we got a force of gravity here. All right, so we got to calculate those two things. Okay, so we got 4 times 9.81, so 39.24. And then we got 7 times 9.81, so 68.67. All right, so now that I know those two forces, I essentially want to simplify this to look like this. Right? That's really what's going on here. 11 kilograms worth of mass is being pulled in two different directions by unequal forces. So I want to find net force. That'll be 68.67 minus 39.24, okay, which should give us 29 point, I forget, 43. Right? All right, so our net force is 29.43 newtons. Now I want to calculate the acceleration, and this is the part that people screw up on a question like this. Okay, that's going to be F net divided by mass, and it's the mass of the system that we use here. So 29.43 divided by 11 kilograms. That gives us 2.7, because we only have two significant figures here. Actually, we only have one significant figure here, so this is going to be 3. Okay, so the acceleration is going to be 3 meters per second squared, and because it's for the 4 kilogram mass, it would be up.
If that question was asking for the mass of the system, would you have two significant digits? I mean, not the mass of the system, but the acceleration of the system, would it have two significant digits?
Yes. Yes, it would, because when we add numbers together, it goes by decimal places. So yes, we gain a significant figure there. We don't gain accuracy, but we gain a significant figure. Yeah. Probably wouldn't give you one where something that strange happens. Yeah. Absolutely. Okay. So let's say we have Earth, Moon, Sun. Okay. I want to find the net gravitational force on the Moon in this question. Okay, so I want to find the net gravitational force on the Moon. Okay, how many calculations is that? 3 calculations. So I'm going to give you about 3 minutes, because that's about all it should take. Okay. Sorry, we need sun, moon distance. And that is 1.49. 1.496 times 10 to the 11 meters. Do we normally just walk in? So the 3 calculations we have to do. We have to find the force of gravity between the Earth and the Moon, the force of gravity between the Moon and the Sun, and subtract those 2 numbers, right? Because they're pulling in opposition to each other when we find the net force on the Moon. All right, so we're going to have force of gravity between Earth and Moon. All right, so that'll be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 7.36 times 10 to the 22 divided by 3.85 times 10 to the 8 squared. All right, so that'll get us the force of gravity between Earth and Moon. All right, so we're looking at 1.98 times 10 to the 20 newtons. All right, so that's force of gravity between Earth and the moon. Now we got to do the same thing for the moon and the sun. Okay, so we will have 6.67 times 10 to the minus 11 times 7.36 times 10 to the 22 times 1.99 times 10 to the 30 divided by 1.49, is it 1.496? Yeah, 1.496 times 10 to the 11 squared. Okay, so we're getting 4.36, yeah, 4.36 times 10 to the 20, did I put that all in? 130. Yep, okay, so 4.36 times 10 to the 20. Okay, so the moon is more attracted to the sun at that point than it is to the Earth. And the moon actually does like wobble out, okay, when it's going through on that part of its orbit, okay, and then it comes back in, okay, once it starts to move back around. Right? We don't have to worry about losing it to the sun anytime soon. Okay, so we just subtract those two numbers, and then we would have our net force. Okay. All right, so our net force is 2.3 or 2.4 times 10 to the 20 newtons towards the sun. Actually, we have three significant figures, 2.39 times 10 to the 20. Okay. All right, what else do we want to go over there, guys? Kelly? What kind of graph? Okay. All right, so back in kinematics. All right, so we've got time in seconds. We have velocity in meters per second. And we're given a velocity versus time graph that looks like this. All right, we want to find the overall displacement from this graph. Okay, now remember that displacement can be calculated by taking average velocity and multiplying it by time for each section of the graph. Okay, so that's what we're going to do here. Give you a few minutes on that one. So as I was saying before, what we have to remember here is that we want to use average velocity times time. That's easy when we have a place where the velocity isn't changing, because like for this part here, between 2 and 7 seconds, the average velocity is 2 meters per second, right? But it is a little trickier when we have a place where the velocity is changing. Okay, this object is slowing down here in the first 2 seconds, but it goes from 5 down to 2. The average velocity is halfway between 5 and 2 because this is uniform acceleration. That's why we go base times height over 2. Okay, is because that gives us the average velocity times the time, which is the base of the triangle. Everyone kind of following me there? All right, so I've got to identify the shapes that I want to find here. I would say this rectangle all along here, okay, is probably an important one. This triangle here is one that I would need to find. This little triangle here is another one I would need to find. This triangle here, and then finally this rectangle. Those are the shapes that I would have to find. So for our first triangle here, right, it has a base of 2 and a height of 3, right? So 2 times 3 is 6, divided by 2 is 3 meters. This rectangle here is 7 seconds on the base and 2 high, so it's 14 meters. These are both positive numbers. Then we have this small triangle here that's 1 second on the base and 2 high. 2 times 1 is 2, but divided by 2, okay, that triangle has an area of 1 meter. Okay, and then we have this triangle here down below that has a height of 3 and a base of 1. Okay, 3 times 1 is 3, divided by 2 is negative 1.5 meters, because the height of the triangle is actually negative 3. And then for this rectangle, it goes from 9 to 12, and it's 3 high. 3 times 3, actually negative 3 times 3 is negative 9. So then once we have those numbers, then we just put them all together. All right, so we have 3 plus 14 plus 1 minus 1.5 minus 9. Okay, so our total displacement is still going to be positive 7.5 meters. Okay. That could very easily be, a graphing question could very easily end up in the multiple choice or something like that, where, I ask you to interpret it, tell me what's going on, or do a calculation. Probably wouldn't be that many steps if I was asking you to do that kind of calculation. The graph would probably only have 2 sections, okay, just so you can show me how to do it, show me that you know how to do it, and then move on. Okay. All right, what else? A static question? Yep. Okay, so I have this 250 kilogram sign hanging from 2 cables that are attached to 2 walls. The angle between the cables is 120 degrees. I want you to calculate the tension in either one of those 2 cables. Doesn't matter which one, because they are equal. Okay, but find the tension in one of the cables. So the thing we have to realize to get started on this is that the net force in this question is what? Is 0. The sign's not moving. Okay, so there's no net force here. Okay, there are forces involved, obviously, but they all add up to 0. So I have a force of gravity acting down. That's 250 times 9.81. Right, so it's 2,452.5. newtons. Now, there's 2 cables, but they're pulling at an angle. If they're pulling at an angle, that means they each have a horizontal and a vertical component. Agreed? Okay. So essentially then, they each have a triangle that looks like this. Okay. So this angle in here would then be 60 degrees for each one of them. This side is essentially the horizontal force that's pulling against the other cable's horizontal force, and it balances out to 0. Okay. What is this force, the vertical force, for each one of those cables? Right, half of the force of gravity. Okay? For each one of those cables, their vertical component is half the force of gravity. That way it adds up to the force of gravity and gives us a net force of 0. No, you could have drawn them this way. Yeah, either way it would work, because the cos of 60 and the sine of 30 are both 0.5, so you get the same answer one way or the other. All right, so this side here, okay, is going to be 1/2 of 2,452. Okay, so 1,226.25. All right, so now that I know one side of this triangle and an angle, can I find the hypotenuse? All right, so I know the adjacent side to this angle, and I'm looking for the hypotenuse. So that's going to mean that the hypotenuse will be the adjacent side divided by the cos of 60 degrees. So that'll be 1,226.25 divided by the cos of 60, and that will give us 2,452.5 newtons, because the cos of 60 is 0.5. Okay, you had one just like this on your Newton assignment, and it threw you because the answer was the same as the force of gravity for the light. It was a lamp, okay, being supported by two cables, okay? And a bunch of you had your work there and you had scribbled it out, and I looked at them like your work was all right, but you didn't like that the answer came out to the same as the force of gravity, okay? It just messed with you because I happened to pick an angle that was going to give you a number that you just didn't believe could possibly be right, okay? I probably won't be quite that cruel on your final, but okay. Understand that sometimes stuff like that happens and you probably did it right, even if it doesn't seem like it. Okay. All right, what else? What other questions have we got? Okay, what kind? Angled or off a cliff? Angled? Okay, so we're looking for max height and total horizontal distance. Give you a few minutes to get ahead of me. 40 degrees, 400 meters per second. All right, so we always have to break up a projectile motion question into its vertical and horizontal parts. Okay, what's the one thing they share? Time, right? Time is the same for both. All right, so this side of the triangle here is going to represent our initial vertical velocity. This side of the triangle here is going to represent our horizontal velocity, which is constant throughout the entire flight. All right, so V horizontal and VI. All right, so I'm going to calculate VI. It's the opposite side of that triangle, so I'm going to go sine of 40 times 400. Okay, so we've got 257.115 meters per second, and that's going to be upwards. And then we'll calculate the horizontal one. So cos of 40 degrees times 400 gives us 306.418 meters per second. Okay, what do I have to remember about the whole trip in terms of VF? It's the same, but negative, right? Okay, so VF is negative 257.115 meters per second, right? And we know the acceleration is negative 9.81 meters per second squared, right? We can find time then with this information. Okay, so we'll take our 257.115 and divide that by, sorry, we multiply it by 2. We're subtracting it. Okay, we're subtracting negative 257 divided by 9.81. All right, so our time is 52.426 seconds. All right, so that can come over here, 52.426. Okay, and then we can calculate the horizontal displacement by going v times t All right, so this thing is going to travel 1.6 times 10 to the 4 meters horizontally. Okay, everybody all right with that? Okay, what changes if I now want to find the maximum height? Okay, so what does VF change to? To 0, right? At the maximum height, VF vertical changes from this number to 0 meters per second. All right, so I'm now looking for D. Okay, that's my question mark. So I'm going to use VF squared equals VI squared plus 2AD. That's the formula that I want to plug in now. Okay, solving for D. D will be VF squared minus VI squared over 2A. So we'll have 257.115 squared divided by 19.62, right? Because VF is 0. So okay, so it's going to reach a maximum height of 3.4 times 10 to the 3 meters. Okay. Okay, what else? Off a cliff, yep. Okay, so I have a 51 meter high cliff. Object goes horizontally off that cliff and hits the ground 25 meters from the base of the cliff. I want to know how fast was it moving when it went off the cliff. Right? So it doesn't seem like I give you very much information, but in actual fact, I give you quite a bit of stuff here. What else do I give you vertically? What's that? VI? What's VI? That's the thing you have to realize. Okay, you can't solve one of these if you don't realize that if something drives horizontally off of a cliff, that its vertical velocity initially is 0. All right, and what else do I know vertically? Acceleration, right? So 9.81 meters per second squared. Okay, I don't have to make that negative. If I do make that negative, I need to make the 51 negative as well. Okay, but since there's no change in direction, I'm going to leave it all positive. All right, what do I need to find if I am going to find V, which is what I'm looking for here? I need time. All right. Do I have a formula that has A, VI, and D in it that will also get me time? You remember that one that we didn't use on the space shot? Jab, 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 jab. Okay, yeah. So this one, D equals VI times T plus 1/2 AT squared. That'll get us what we need, especially since VI is 0. Okay, all we have to do is manipulate for T. So D divided by 1/2 of A square rooted will get me T. So square root of 51 divided by 1/2 times 9.81. Okay, so we've got that. We got to square root that. Okay, so our time is 3.22 seconds. Now that we have that, okay, we're looking for V. So we're going to go 25, the distance, divided by the time, 3.22. Right? This thing drove off the cliff at 7.8 meters per second.